Karen Grove, and she was at San Francisco State in 1989. Before that, she got her BS in geology, structural geology, in the University of Maryland. Any University of Maryland folks here? Terps? There's Terps, isn't it?
Terps.
Yeah, Terps?
Absolutely.
All right. And in 1989, she got her PhD in geology at Stanford University. Any Cardinal? Oh, come on. And then started her position at San Francisco State. She's worked with many different students, 26 undergraduates, 8 MS master's students completing their theses. Just a ton of work around California. Worked in Point Reyes. Some of you have been looking at some of the uplift there based on the terraces. But also has done a lot of pedagogy as well, looking at, she invented with another colleague what is known as just-in-time teaching, and they will put that into practice. And also...
Sounds like Russell.
Yeah, just-in-time teaching, yes. And also had an NSF grant called SF Rocks, reaching out to the community with kids in science at San Francisco. And that was Lisa White previously mentioned. So a lot of work both on the research side, but also on the teaching side as well. And she's incredibly well-rounded, as you can tell from her background. And she continues to stay very, very busy, as her husband can attest to, and traveling all over the world, from Argentina to Chile to pretty much all over. But we're going to hear today about San Francisco and some of sedimentary rocks that have been recently uplifted and exposed along the beach. So with that, I'll give you Dr. Karen Grove. Thank you very much.
Thank you. And these are not rocks, by the way. We call it mud, sand, and gravel.
Sediments.
They sort of hold up the cliff, but just barely, because they're really young. So thanks, Todd. Yeah, I retired from San Francisco State, well, almost 3 years ago now. It seems hard to believe. But, you know, a geologist never stops being a geologist, so I still am super interested in geology and trying to keep some of the stuff we did alive. I teach for a lifelong learning institute now where I live in Ashland, Oregon, so there's still plenty of ways to stay involved. Terry Mcguire, this was his master's thesis, and actually he finished it now probably about 10 years ago, and then went to Houston, has been in the oil patch ever since then. But I thought it would be fun to talk about it because he went to work right away, and so we haven't really gotten it published. So I thought, well, you know, I need to get it kind of out there. And if anybody, he actually did a really nice job with the thesis, and it's all PDF. So if anybody is interested, you know, there you can get a hold of me, and I'm happy to just make the thesis available if you like. It's got all the well logs and cross sections and that kind of stuff. Lots of diagrams to look at. Not quite as many words, which is kind of fun. So we're going to look at the controls on sedimentation of both tectonics as well as global sea level, because we're looking at the Pleistocene. Of course, you probably know that was a time that's characterized by rising and falling sea levels, as we had glacial and interglacial cycles as we've been in our current ice age. And so we're looking, let's see, I think maybe I'll go, let's see if I can figure this out.
That's on my right. There.
Oh, okay. Yeah, I just have to figure out there's a delay slightly. So the reason we did this, beside the fact that it's literally in our backyard, right? This is like the sediments we're sitting on top of at San Francisco State and that are right out at the cliffs. But amazingly, at that location, right there in San Francisco, you know, it's part of the San Andreas fault system, and there's a lot that wasn't understood, and in fact that still isn't understood, but we at least shed some light on that in terms of just understanding that whole system a little better. And the San Francisco Public Utilities Commission, which is the agency in San Francisco responsible for the water supply of the city, was doing a lot of work. They have drilled a lot of wells, both for monitoring as well as for production of water. And, well, who knows where most of San Francisco's water comes from? Hetch Hetchy, right? So that's San Francisco way back when, built a reservoir just north of Yosemite, drowned the Hetch Hetchy Valley, and that's where the majority of the water for the city comes. But this groundwater basin, they actually do put a small percentage of groundwater from San Francisco and mix it in with the Hetch Hetchy water. And they've been interested in developing that more. Conjunctive use just means, you know, try to use it a little more. For example, trying to make sure that the aquifers are really full when we have really wet years, so that there would be emergency supply available in drier years, or, heaven forbid, you know, an earthquake that severs, you know, the pipes that are bringing the water from the Sierras. And of course, Terry was looking for a project, so given that he was looking at going into the oil patch, working with well data and oil crops was, I don't know, I don't seem to be doing that very well. Let's use the tried and true. So what we're going to look at is briefly the geologic setting. We'll look at the outcrop belt, the sediments that are exposed along the coast, and then the methods that we use for correlating. Well, okay. I'm going to put that thing down. Just
step away from the pointer.
Wait, why is that? Oh, that's interesting. So there's one that didn't. There, okay. The methods that we use to correlate between the outcrop exposure and the subsurface, the sediments in the subsurface. And then, I mean, the structural story is basically that we had a basin that was subsiding rapidly in the Pleistocene, and that now is being uplifted and exposed so we can study it and figure out what happened. And then we'll just look at the paleogeography that we were able to establish based on the correlations that we did in the aquifer potential. And then finally, how do these sequences that we see correlate with global sea level? So we'll end with that. And if you have a question as we go along, you know, please feel free to ask. So how many of you know this part of the world here, Western San Francisco? Have walked on the beach there or something? Lake Merced, so here's the west coast of San Francisco, and Lake Merced is basically, this is the end of San Francisco, and then we're into Daly City, San Mateo County. But Lake Merced is kind of keep your eye on Lake Merced. That's a good for, you know, to figure out where we are. And San Francisco State is just here directly east of Lake Merced. The orange is the outcrop belt of the Merced Formation. And so it is exposed. So what's the west coast of San Francisco look like? Like, is it cliffs or beaches? Beaches. But as you go south, you start getting into cliffs. Cliffs that keep rising in elevation until you get to Muscle Rock, which is where the San Andreas fault comes out. And that truncates the Merced Formation there. It was probably much more extensive, but this strand of the San Andreas just became active about 1 million years ago. So this is called the Pilarcitos Fault. We can't see it here, but I don't know why does that seem so sensitive to me, but it does. So it ties into the San Andreas here, and this was the active strand up until about 1 million years ago. And then this one became active, and of course anything that was deposited here has gotten removed because of that, that activity on the fault. And one thing that's super cool is this whole unit is dipping northeast. So what that means is, and we'll look at a cross-section of that, but you walk along the beach and you just go right up through the entire section. So it's a pretty cool thing. And it's almost 2 kilometers all in the Pleistocene. So it's a real amazing sort of world-class preservation of Pleistocene sediments, which is one thing that makes it really, really cool. So otherwise, of course, San Francisco has a lot of Franciscan formation. That's Franciscan complex. That's the bedrock, and then some other a little bit older sediments. But the Merced's pretty much all Pleistocene. Okay, so this is that photo, but without all the words to put us in perspective a little bit. So here's Golden Gate Park. The Golden Gate Bridge is just right off here, just off the picture. Here's San Francisco State University. Here's Lake Merced. So the Merced is exposed basically from about here and then going south to where the San Andreas Fault comes out into the ocean at Muscle Rock. And then it's offshore here and comes back onshore at the Point Reyes Peninsula, and then of course continues a little bit more to the north before it ends at the Triple Junction. This actually, I don't know, published about 10 years ago, I guess. Well, maybe a little more, 12. The USGS did a whole lot of seismic surveying out here, and it turns out this is just like a mess of faults. Mess of faults. Lots of interacting fault strands. And so like today there's a little extensional area here because of a step over from the San Andreas to another fault here. There's a transpressional area here, lots of like little reverse, little fold and thrust belt. So it's super complicated, but we'll look in a map to see how the Merced kind of fits into that evolving, geometry of, I'm used to it going off, of interacting faults in this area. So, first thing I have to do is give, oh man, why? Okay, I said I was not going to use that, and I'm going to just go with that. I have to give kudos to 2 guys, Ralph Hunter in the upper left and Ed Clifton in the lower right. They are sedimentologists who were scientists at the U.S. Geological Survey, and they spent, I just can't even imagine how many hours describing this entire 2 kilometers along the coast. And so I'm going to show you. So this picture is showing what it looks like as you're heading south from San Francisco along the coast. And those cliffs with the Merced Formation sediments are exposed as they get higher to the south. And of course here, this is a low tide winter beach where a lot of the sand has been removed. And so sometimes you can see the sediments continuing out into the beach. And we're looking north, so they're dipping, everything's dipping northeast. So there's the dip. That's an apparent dip, of course, but they're dipping south, or north rather, and east.
Excuse me.
Yeah.
Is the Merced Formation the one that fronts Daly City?
It is. Yeah, and so the next diagram, well, the one after this will show the map of it. So this is what Hunter and Clifton did. This is the base of the sequence, so a little over 1,700 meters, and then continues up into the youngest. So these are unconformity-bound sequences. So those wavy lines are the unconformities between sequences. And basically, they just used the alphabet system to give names to these sequences so that they could refer to them. So Z is the Coma Formation, which is just the youngest sequence, but it has a different name because it's the youngest. And then they just went back the alphabet. So like here's A, B, C, D, up to Z. And then they had more, they had almost, well, around 40, so they had to use parts of the alphabet again, so they doubled up LL to ZZ. But the cool thing is they write about them in terms of the sequences, so you can go out on the outcrop and take their descriptions, and you can go, oh yeah, okay, I see that, or I don't see that. And I know you can't see this very well, but mainly, the thing to notice here is that the gray is shelf deposits, continental shelf deposits. So hopefully it's obvious that the lower part of the formation is dominated by shelf deposits. Now, these are the sediments that are exposed in the coastal cliffs today. So what that means is that when sea level was high, the coastline was farther east than it is today, right? Because today, the beach is right there, but there are all these shelf deposits in the cliffs, so the coastline would have been farther east during much of that time. So most of these sequences are regressive. So for example, if we look at this one, it's shelf deposits, and then they shallow upward into, in this case, foreshore and backshore, and this one actually has a little bit of embayment or lagoonal muds on top of it. So it's shallower, then there's an erosional unconformity, you're back in deep water and in shelf depths, and then it shallows upward, shallows upward. When we get into the younger part of the sequence, we don't get so much shelf deposits. It's much more, near shore. So that color is near shore. So surf zone, so like sequence T starts in the surf zone, so it never gets deeper than the surf zone, and then goes up into backshore and coastal dunes. And we see a lot of embayments. So most of what we focused on was actually sequence O to Z. So the youngest part of the sequence of the formation, and you'll see why that is, because that we can correlate it inland, whereas this older stuff, we don't find it inland at all. So this is what we see in the well data. Are these sequences. And I'll show you some sediments just to see what those look like.
Is it known where the equivalent shorelines were on the other side? Is it known where the equivalent shorelines when these were mainly shelf?
No, because it's, let's see, maybe let's go back to this. Because the thing is that we don't have Merced preserved to the east of it. So, yeah, don't know. And of course, in San Francisco Bay, when they built the bridges, they drilled wells down into the bedrock to see what they were going to build a bridge on. And I think it was about 4 sequences of sea level cycles. So when sea level is low, San Francisco Bay was a river. And when sea level was high, it was bay like today. Yeah?
Can you go to the slide that's after this one?
I'm sorry?
Oh, I was wondering, can you go to the slide that's after this one? When
Yeah.
you're done? When you're done?
You bet.
Oh, the one with the 1700 meter.
Oh, yeah.
The map.
That one.
Yeah, that one.
Yeah. Did you have a question or?
Oh, no, I'm just taking notes on it.
Oh, okay. Okay, cool. Excellent. Yeah, one thing, I know you can't see the legend, but basically, blue is always mud, okay? So if you see blue, you know it's mud. And it's going to be embayment mud, so like an estuary or a lagoon. If you see these yellow colors, it's sand. So near shore, foreshore. In other words, the surf zone and the swash zone. And then these two are dunes, so backshore, the green and red are backshore, just like the flat beach, as well as coastal dunes. And yeah, the shelf is gray, and these we won't really see. Okay, so here's the map. This is Mussel Rock. So north is to our left and south is to our right. And so again, here for reference, this is Lake Merced. And so here's sequences Y to Z, U to W, T to R, and to Z. Well, the units are kind of flat through here. And then P through J, and then the older stuff down to the San Andreas Fault. So this is, well, this is actually John Daly Boulevard now. So this is all Daly City. San Francisco ends about here, Daly City. And then where the San Andreas Fault is, that's in Pacifica. Does that work? And then the strike and dips are just, you know, showing the general orientation, the attitude of the unit. There's some folding within it, but mostly it's a monoclinal sequence along the coast, which, as I was saying, is so great because you can just literally walk along the beach and go through the entire sequence. So it's pretty cool thing. Does that make any questions so far? So yeah, this way, of course, I taught Sed Strat, like Todd does, and so I would take my students out here, but of course we didn't go through all these sequences. We pick a few and use those to illustrate the different environments, because it definitely gets, like, you walk along and you're like, oh my God, which sequence is that? It's pretty crazy. So this is the upper 1,000 meters or so of, well, actually 1,000 feet. This is meters. You know, when you're using well logs, they're always in feet. And so you're always in that dual world. So yeah, about 1,000 feet or a little over 300 meters. And this is the section, the upper part of the Merced that we focused on for this study. And so Hunter and Clifton, this is grain size. So just there alone, if you can imagine how many, and that's just the upper little part of the formation. So a lot of samples that they did grain size analysis on. And then inferred water depth. So deeper to the left and shallower to the right, inferred from the sedimentary structures and grain size and so forth. And so the red is these unconformities, again, between these sequences. So like O was one that I did with my students because it was really complete. You went from the shelf into the nearshore surf zone, into the foreshore swash zone, and then into the backshore beach. So it was really nice one to see that sequence. The other one we would always do is R, where you had a beautiful embayment deposits exposed, and then the embayment got filled in with backshore sand dunes. So we're going to look at just some examples of what those sediments look like in those sequences. Uh-oh, that didn't work. Well, it works on my Mac. Okay, well, so it showed up on my Mac. Interesting. So what I'm showing there, if you could see it, is imagine one of these regressive sequences. So let's say it's O, where it's shelf, and then as you go upward, it becomes shallower up into the beach, backshore, right? So what would sea level, so if you're in the shelf, is sea level, are we going to be in a time of high sea level, in other words, an interglacial period, or a time of low sea level? High sea level, right? Because we're in deep water. So the shoreline's farther east of us, we're sitting here on the shelf, and with time, sediments fill in, sea level goes down, and there we are at the beach. So we're preserving that falling part of the sea level curve. And then on top of that, we get this erosional unconformity, and you go from the beach directly to shelf deposits. Snow intervening, near shore, or foreshore, boom. What happens? Well, sea level is low, and you've got that surf zone going. As sea level rises, the surf zone's moving across the shelf going much, much, much. I call it the Pac-Man surf zone. Much, 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 much. And it just erodes everything. So all you retain, and sometimes you get a transgressive lag, just a gravelly lag there, but you don't see those intervening environments because they all just get eroded away. So then sea level is high, and you preserve the regressive sequence as sea level falls. But then when it comes back in again, munch, 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 and you just get an erosional unconformity. Is that okay? That was more fun than the diagram. So what it was showing is that you just preserve the fall, and then you don't see the rise, and you just have an erosion, and then you preserve the fall again. Okay, so this is sequence O. So this is an example of what the shelf deposits look like. They are laminated from just settle out of suspension to massive, because a lot of the sediments, organisms crawl through it, so the laminations get destroyed by bioturbation. So a lot of it, in fact, in here we can see these are all clam shells, and so all of that is just massive because it was thoroughly bioturbated by organisms burrowing into it. And generally has these kind of gray, green, kind of yellowish green colors. And that's in sequence O. So then above the shelf you often find nearshore deposits. So this is the surf zone. So you have migrating megaripples, ripples that are about this high, and that creates extensive crossbeds. And that's also, of course, the coarsest grained sediments, where you get some gravels, because the surf zone is the high energy part of the system, right? Once you get beyond the surf zone, it's settle out of suspension, and in the surf zone, you're getting constant wave action, moving ripples, megaripples, back and forth. And so you see a variety of directions, because the megaripples can move in a variety of directions. And then above the near shore, we see the foreshore, and those are always planar, so that's the swash zone, right? So high velocity sheet flow, where the waves break, and then you just get that planar swash and back swash. And so, I don't know, can you see the planar beds? Are they visible there? Enough color differentiation. Sometimes, if you don't have the color, you can't see them very well, but. And then above that, you will have the backshore, the beach, dunes, sand dunes. Some of the sand dunes have turned into paleosoils, where they've just sat there and weathered. You see a lot of hoof prints. You see ones that are probably like horses. Hunter and Clifton found dog prints of some sort. I don't know, maybe they were wolves, I don't know. This one they think was a mammoth print. And they have found mammoth bones in the unit. So it was the Pleistocene. There were some big critters moving around on the beach in those days. And then as we get into this upper part of the formation, we have mostly embayment and associated environments, and I'll show you a paleogeography map to show how that looked. But for example, in sequence R, we see ripples that are draped and bidirectional from being deposited on tidal flats. Then we see tidal channel deposits that are more massive, lots of broken shell material. And then this modeled unit with root casts, that's salt marsh. So as the embayment is filling in, it becomes marsh, and then over top of that is backshore, basically beach and dunes as the embayment filled in. And we see that over and over again in the other sequences. Okay, so here's the paleogeography map, and this is already assuming we've done the correlations, but we'll go to the correlations next. So basically, I've been showing you units exposed out here along the coast, but what we were doing was correlating the sequences here with the sequences in the subsurface using water well data. And so what they show in this upper part of the Merced is that we had a persistent estuary, actually where Lake Merced is now, but it was sometimes quite a bit bigger. But we had coastal dunes that were creating the estuary. Nothing nearly as big as San Francisco Bay, right? This is a much smaller scale, like coastal lagoons that you see, or little estuaries that you see along the coast today, but pretty small scale. Because this is, yeah, that's, like here's our campus, and there's Lake Merced. And then salt marshes were forming along the edges. This is alluvium, so we had alluvial fans that fed alluvium in to the little embayment. And a fairly persistent tidal channel at that location where today the zoo is. And so this, again, is a result of the correlations, and I'll show that next. But one thing is that the coastline was oriented a little more northwest than it is today, and we'll see that in the correlations.
What's the age about?
So we'll look at the age, what ages we have. So there's an ash, the Rockland ash is here, and it's about 500,000 years old. So to just give a, kind of, that's about 500,000 years ago. The dating through the rest of it is, it's fossils, and some of those have pretty big range, some of them are still extant. So it might go into the very end of the Pliocene, but I don't think it's certain. We think most people think it's wholly within the Pleistocene. In other words, the last roughly 2.5 million years for the whole thing. But yeah, we do have that date here of about 500,000, and we'll look at the ages a little bit more toward the end. So these are what we did for correlation. So this is that exposure along the coast, as if we were offshore looking back toward the coast. So here's the oldest part of the formation. There's a bunch of landslides here on the surface, which is why it looks kind of white. But we do have a couple really deep wells that are behind the landslide. So we have some really good data points right there at the coast, even though it's a bit of a mess at the surface. But in the north and south, you can follow it really well. So these red dots are where San Francisco had developed a well, either as a monitoring well to monitor water quality or for production of groundwater. And so we were able to get those data, and we got some funding from the Public Utilities Commission for the project. And so I'll show you some of the, I'll show you a couple examples of the well data, and also these correlation lines. I'll show you a few of them, not all of them. And the Rockland ash, because that was like the one marker bed, is like real important. So we had electric logs, we had the drillers' logs, so the driller's description as they're drilling, and they say, say what things are. But Jerry was able to sort of high grade those with his own description. So we also had well cuttings. So every 10 feet they would take a sample while they were drilling. And so we had bags every 10 feet. And so basically he just took a little piece from each bag. So it's like a pseudo core. So every 10 feet, and so with a glance you could look at what was happening up section by looking at these little bits of cuttings. Not good as a core, but then this stuff isn't consolidated to make a core anyway. So here's an example. So for all the wells that we had, Jerry put together these just really awesome logs that included the lithologic description from the drillers' descriptions, along with his own observations. And then this is a gamma log, electric logs. But for example, the blue is the embayment mud, right? So you can see a big kick in the electric logs where the mud is. And you see kind of a gamma ray kick too. So basically what we were trying to do then was, we know the sequence boundaries at the coast, and we're trying to figure out, where those sequence boundaries are in our wells. And that was a little tricky, but we had a couple other things that helped with that, and I'll show those. Oh, I should mention, so this basically shows the aquifers. So the great thing about the embayment mud is it creates the aquicludes. And so there are three kind of main aquifers that are more or less continuous. The V, which is confined because it has muds above and below. The X, which is mostly confined, and then the Y, which is unconfined. So that basically goes right up into, becomes the bottom of Lake Merced. So it's interacting with the meteoric water that's coming down at any moment. Okay, so here are the cross sections, and I think the next one is going to be, this is a really good one to look out. I know there's a lot going on here, but the thing, let's see, let me just see what the next, yeah, okay, great. The structure's kind of crazy, and I'll show the structure a little more in another slide. But on this one, this location right here is the hinge line of a fault propagation fold that we'll see really well on in this cross section. So here, this shows a thrust fault. There's a thrust fault along the east side of the unit that's exposed at the surface as you go to the south. But as you come to the north, that thrust fault is not exposed. It's still blind. And all we're seeing is this big fold in the hanging wall of the thrust fault, but the thrust fault itself has not yet made it to the surface. So this whole system is migrating north with this contraction that's uplifting the unit from south to north. And so that was the real challenge, was to correlate over this pretty big structure, which we'll see in a minute. And so figuring out the sequence boundaries was essential, also because, I mean, if we look at the paleogeographic diagram, facies are changing, right? So if you try to correlate, the near shore, it's going to be transgressive through time. So this would be like one moment of time. So the facies are varying pretty rapidly laterally, so we need to look at the timelines, which are the sequence boundaries. Okay. This is a map of the basement, the depth to basement. So in other words, under these sediments, there's Franciscan bedrock. right? And that Franciscan bedrock drops off like crazy right here. So these are in feet. So here's 0, in other words, sediments are covering the bedrock to here, and then above 0, the bedrock is exposed above the surface. So the sediments are getting thicker because the bedrock surface is diving down, and so within, what is that, about a mile, bedrock is going from 0 to 3,500 feet deep. So it's like a major precipitous, and so what we think, so that's where this thrust fault is now, but that's where it would have been a normal fault. When the Merced was being deposited, we had normal faults, right? How was the basin subsiding? Normal faults. That was causing this basin, it was subsiding very rapidly to collect all these sediments in a couple million years. And now that is being inverted, and that'll show up a little better on the cross section. This is just to show a little bit of the complexity of the faults offshore. So this is an extensional basin today, where it seems that the San Andreas, sensu stricto, is stepping over to the Golden Gate Fault, creating an area of extension here. Actually, the San Gregorio Fault goes up into a whole bunch of thrust faults here, folds and thrust faults. Small scale, but nevertheless there. Here's the San Andreas today. This was the San Andreas until a million years ago. Now this is the big player. And so the geometry of these interacting faults was such that there was an area of extension for quite a long time here. And it was certainly much, much larger than this. It was a much, much larger scale feature. And we were going off, we were full oceanic conditions off to the west.
Take that.
Take that. But here is where the Serra Fault, well, and these probably shouldn't all have teeth on, but here we actually see bedrock lifted up onto quaternary sediments. So the thrust faulting has made it to the surface. Here, we're just starting to see that, and like I say, here it's still blind, so it's still underneath lifting things. So it seems like this whole system is propagating north. The extension is now farther north, although at a much smaller scale. And then in its wake, we're getting a pulse of contraction. Does that make some sense? Questions? So actually, I think I'm just going to leave that. But this is basically where, if we could project that blind thrust to the surface, this is where it would be. We see a little bit of a scarp there, but mostly it's blind. Again, this is where the top of the propagation fold would be located, which I think we will see in the next one. Yes. So this is this cross section right here, and so here's our bedrock. Here's bedrock, and where it's just dropping off precipitously to the west, and here are some of these older sequences. Shelf dominated, again, blue just means mud. And the thing is, the reason we concentrated on these younger sequences is because that's when they start to be preserved to the east. Here's Lake Merced. And so these older ones, whatever was there has been eroded away. We don't see any of it. They end there. But starting at S, that's where we think that we are seeing the sequences going across to the east. A couple critical data points, because you could draw that almost anyway, but we had some real control. And happily, let's see, this would be, let's see if I can point this out. there, let's see, where are those little striking dips? Oh, there they are. Like right here, this is actually an exposure of the Rockland ash, our marker bed. And so that's an essential data point right there. There are a couple of places here where we had the Rockland ash exposed on that eastward limb of that fold. So that was really important for getting this geometry here. And of course, we accounted for if it's a parent dip and all that good stuff that you know in structural geology, right, Ann? So these heavy black lines are the sequence boundaries as we were able to interpret them. And so, again, yeah, here the aquifer units would be the white in between. The white is basically mostly sand, the blue mud. So we can see the layered aquifers in the area around Lake Merced.
What's the reddish color on the right?
Yeah. Yeah, that's the alluvial fans. So the elevation, these go up into the hills of San Francisco, of course. And there are, of course, you can't see them now. There are alluvial fans coming out there, now covered with houses in the Sunset District. But yeah, alluvial fans, that would be the edge of alluvial fan kind of coming down into the flatter part where the embayment was.
So you can see the equivalent shorelines for the younger units.
For the younger units, yeah, right. For the younger units, because the thing is, for the younger units, we aren't really getting into shelf depths.
Right.
So we've just got this sand dune, embayment, a kind of alluvial fan, backshore alluvial fan system. So it's a much more confined, much more scalable sort of thing. But yeah, but the older ones, we don't know.
So the bottom, that's fault then, right? Yeah.
So this is the bedrock contact, but yeah, almost certainly this was a normal fault given the way it drops off. And I mean, we don't know exactly where the thrust fault is. I mean, we're saying this thing is inverted. One fault, two faults, you know, this is a little bit interpretive. We know this, and we know it's being inverted. So now these are thrust faults, and this is our fold propagation, our propagation fold over the thrust faults. But I don't actually remember how that one got there.
Active.
To tell you the truth.
Very active.
So these, yeah, very active, yeah, because these are what are today uplifting and making the cliffs. Yeah, totally. Yeah, so this is just, again, to remind us that in this upper part, we're really dealing with this embayment system. So the embayment created by coastal sand dunes, and then, you know, with an inlet and alluvium coming down from the hills and salt marshes around the edges. And yeah, that's just to show that there were embayments in roughly the same location, give or take, throughout those sequences. This cross-section is A to A prime, which basically is parallel to the coast right here. So this would be Lake Merced right here. And we're just kind of cutting at a weird angle, that escarpment in the bedrock. But what this is one of the reasons why we think the coastline was oriented a little more north-south, northwest, southeast than it is today. It's almost due north-south. Because this is all backshore, so all sand. When we get up into actual San Francisco in the subsurface, it's pretty much all backshore sand. So sand good for aquifers, but not good for trapping. Not good for having aquicludes. So the thing is, you can have a deterioration of the water quality because you're getting a lot more interaction with surface processes. So the best aquifers, the best layered aquifers are in the central area where you have embayment, backshore, embayment, backshore, embayment, backshore. And then BB is going the other direction, showing us what happened in the other direction. So BB, maybe, no. Okay, B, B. So at a kind of funky angle to the coast. But this is showing, this is a lot of alluvial fans down here. So again, mostly sand and gravel. So not good for layered aquifers. Best right there. And that's just showing that main cross section again. But one thing that's kind of cool is a lot of coastal places are concerned with saltwater intrusion, right? But the cool thing is that because all of these older units that are being uplifted are really dominated by mud, the shelf muds, they actually block the saltwater intrusion. So we have a nice little block there that keeps, well, here's the ocean, but we're keeping saltwater from coming in because of all that mud that's getting uplifted, those older sequences. Okay, age. So there's a picture of the Rockland ash. It varies from about this thick to about that thick. From around Mount Lassen, it's a very widespread ash, so it's a really good correlation unit because it's found fairly extensively in Nevada, Northern California. And the problem is the ages are a little bit, we have a little bit of a range of ages in the different studies. And so the ages range from about 450 to 600,000 years, which is a pretty big range for something that's 500,000 years old. And so that has yet to be resolved. And that's in sequence S. The other thing that we have is P below it, so it's OPQRS. So there's a few sequences between S and P. There's a mineralogical change, and that's kind of a cool thing, because that is when we think the bay opened. So the Sacramento and San Joaquin rivers were, prior to this, draining out to the south, coming out probably where Monterey Bay is today. And around 600,000 years ago, there was a lake, Corcoran Lake, that was in where the Central Valley is now, but that broke through about 600,000 years ago and drained the lake, and then the rivers, the whole Sacramento, San Joaquin Delta, and all of those rivers started draining through the Golden Gate. And so you actually see a change from local mineralogy of the Franciscan to mineralogy that reflects now seeing Sierran minerals in your own backyard.
Does the Rockland ash, does it extend as far south as like Montera? If you see that all the way through Montera and almost to halfway?
No, it doesn't. No, I don't think Montera is old enough. But there, yeah, it's not at Montera. It's the only place you see it along the coast, I think. The other exposures are inland and more to the north.
Okay, thank you.
The other ages we have are from strontium isotope data in forams. And, oh yeah, we're about done. Well, in any case, this is the last few slides. So 600,000. We don't have space in time for all those things. So this shows our sea level curve back to about 1,000 years ago. And so the ranges of ages based on the previous slide. And then we just did a couple models of trying to do that correlation using a couple different estimates of the Rockland ash age. One thing's clear, here's the sedimentation rate, the accumulation through time. The sedimentation rate is decreasing because subsidence is decreasing as the normal faults are transitioning into reverse faults. And so this all still needs some work, but what we need is a more certain age of the rockland ash to continue to play this game. So that's it.
Any questions?
No,
Yeah, I
there's
have
the,
a question. The rockland ash is kind of a timeline, so how does your
Right.
sequences match up to the timeline of the ash?
well, so the thing is that the range of ages for our timeline are not, it's not super precise. So the ages are ranging from 450 to 600,000 years. So which age are we going to choose?
Well, I'm not so much concerned about the ages, I'm just the timeline. And do you see different depositional environments underneath that?
Oh,
range?
it's deposited in the backshore. So yeah, and at that time, so we're at a time of high and starting to fall sea level, and so that backshore probably continued from today where the beach is back across Lake Merced, and so because the ash was deposited in those backshore deposits, because we see them also, we see it where it crops out in where that fold, it crops out in that eastern limb of that fold that's over the blind thrust fault.
So you don't see the ash in the deep water sediment?
It's a very precise timeline, right? We just don't know what that time is exactly. But yeah, it was deposited in the backshore environment. So it was we were on the beach when that ash came tumbling out of the sky. Now, of course, the other places where you find it were inland, so they weren't in beach deposits inland. But it's a precise time. We're just not quite certain what that exact age is. Yeah.
What did you do to get a better time?
Well, I mean, the thing is that the most recent date, which should be the best, is the older date. And the problem with the older date is that, well, if we look at this, so sequence O is bracketed around about 600,000. The mineralogical change, which would be, that doesn't show up on this, but well, let's look at this one. So we'll choose the 600,000 year age for O. P, that's about 600,000, right about the same time. That's the mineralogical change. Now, if we choose the 600,000 year age for the rockland ash, it's like, how can that be? They're sitting right on top of each other. We must have space to deposit all of, O and R sequences in between there. So that's the problem. The most recent age is the oldest one, which lines up with the dates for O and P. So hence we've chosen, like here we chose 500,000, which is kind of like in the middle. But yeah,
Can you pick up
more
that?
dating techniques are always improving, so that's a good.
So you can pick up the Bruni's-Maruyama boundary in the sediment?
Well, I should say, so this curve is the marine the marine isotope stages from marine data. And so this is marine data. This is what we know. Here's our current interglacial, the last glacial, interglacial, glacial, interglacial, glacial, interglacial, glacial. So these would be high stands of the sea. These would be low stands of the sea. So we're matching up, because our units are deposited when sea level is high and falling. So we're matching up our sequences with the high stand parts of this curve, which is a global curve.
Right.
I mean, that's based on like lots and lots and lots of data from the ocean.
Question not related to the rock menace? Yes, please.
Yeah,
Yeah, I'm wondering about that deeper normal fault. Is there any seismic to show that that's?
there's no seismic through there. There's seismic, I actually brought this is kind of a cool, if you're interested, it's professional paper 1658. But these are the data, the seismic data that they collected offshore, but it doesn't go that deep. So like, you know, they're going a few kilometers into the sediment, but they're not going into the bedrock. So there aren't seismic data that.
Do you think there might be some electricity to that fault?
Surely could be. Surely could be. Yeah.
All right. Well, we definitely want to thank Karen for a wonderful talk. So thank you.